Welcome to the class where we will analyze the stability of nonlinear systems. Today we will consider nonlinear systems with feedback, as shown in the figure above. We will also use the already known linearization using the describing function method, reducing the nonlinear element to the form J of A. And in the shown system, the condition for the so-called limit cycle state is that the sinusoidal transfer function g of j omega is equal to the describing function inverse with a minus. And today this is the most important formula on the basis of which we will solve most tasks. If we were dealing with nonlinear elements with asymmetric static characteristics, we would have to use these two equations below. Today we will be largely interested in graphs in the plane of a complex variable. We will draw both the describing function inverse of the nonlinear element and the Nyquist plot of the linear object. As for the interpretation of when a closed-loop system is stable, I will refer to the Nyquist criterion. In the linear systems, if the Nyquist characteristic covered the point -1, then the system was unstable, and if it didn't cover this point, then the system was stable. It is similar here, except that instead of one point -1, we have a graph. For the part of the graph that is covered by the Nyquist characteristic, the closed-loop system is unstable, and for the part of the graph that is not covered by the Nyquist characteristic, the closed-loop system is stable. However, at the point of intersection of both graphs, we have a limit cycle state. And that's all from theory. Now let me remind you how to draw Nyquist plots by hand. Remind you, because this material should already be available in both laboratories and exercises. However, these rules will only apply to a specific types of objects. Therefore, we assume that in this topic we will only deal with transfer functions that don't have zeros and the gain is positive. These objects will be stable, or marginally stable if one integration occurs. If the object doesn't have integration, we start drawing from a positive value on the real axis. And if it has integration, the graph should start at the bottom in the lower left quadrant of the system. The entire graph passes through as many quadrants as it has inertia number in denominator, and must end at the origin of the coordinate system. On this slide I present what types of tasks may appear at the test. And on this slide I briefly describe how to solve the tasks, but it is more a reminder for someone who repeated material using the presentation. And we will simply move on to specific tasks, based on which I will try to explain to you how to approach this type of tasks. At the beginning, before we move on to specific tasks, let's try to determine the describing function inverse of the nonlinear element . The describing function of this nonlinear element is the content of the task will always include a describing function inverse, or at least components b1 and c1 from which the describing function must be determined. So, the describing function inverse is this is obvious, but let's transform it in such a way that we get a formula on one fraction line without stored fractions. Please pay attention to this minus sign before the fraction line. In the print, it is the same thickness and at the same height as the fraction bar, and there is only a short space between them. I point this out because I had a lot of mistakes of this type that someone didn't notice the minus. Let's multiply numerator and denominator times large A. This fraction in arc sign has to stay. But what can we do to avoid having a fraction under the square root? We can multiply the square root by large A. Then interior of the square root will be multiplied by A squared. So, we multiply numerator and denominator by large A again. And we got a nice form of the describing function inverse. People who have the script can check that this formula is indeed given in the table. Now, when we have this formula, let's try to draw a graph of the describing function inverse in the plane of a complex variable. To do this, we need to calculate where this characteristic will start and where it will end. It will start at the smallest possible amplitude A, and the amplitude of this linear element must be greater than small a to cover all the fragments of the static characteristic that interest us. The arcsine of 1 is the value of the angle for which the sine gives the value 1, and that is 1 second p. And this is the starting point of the characteristic. Now let's calculate the limit for the largest possible amplitude. After substitution, we would have infinity by infinity. So it is better to take large A in front of the brackets and shorten it. The square root tends to infinity and is multiplied by something that tends to 0. We have 1 under the square root, but before the square root there is 0. Arcsine of 0 is 0. So the whole denominator tends to 0, which means that the result is both of these points are real numbers, so we draw on the real axis. This is a final graph of the describing function inverse. Please remember that all points of interest should be marked correctly so that we know their coordinates. In addition, you need to write where the limit is. That is, that large A tends to small a and large A tends to infinity. The last element of the graph that cannot be forgotten is the arrow, which indicates in which direction the amplitude A increases. Please take a look at the second limit. We have transformed the equation practically into the form we had at the very beginning. Some limits are easier to calculate without any transformation. Such tasks, which involve drawing the inverse of a describing function, may appear during the test. Taking advantage of the fact that I have a little more time in the recording, I wanted to show an example of a nonlinear element with hysteresis. For such a nonlinear element, Let's determine the describing function inverse. If someone has the script, I encourage you to see what the formulas are in the table. At first glance, it is not clear where this result comes from. The describing function is But to get a complex number, we have to get rid of the number j from denominator, so we multiply by conjugate. And we managed to get the same result as in the script. Let's now try to determine the real and imaginary parts of the sinusoidal transfer function, p of omega and q of omega. Let me remind you that the sinusoidal transfer function is equal to the transfer function g of s. One just needs to substitute j omega for s. Let's do the calculations for To separate the real part from the imaginary part, one needs to remove the imaginary number from the denominator. As you can see, it is quite time-consuming, but you can approach it differently. Instead of multiplying everything, and then multiplying it by the conjugate, you can multiply every factor in the denominator by the conjugate. The result looks a little different, but after a few transformations we would get the same thing. You can use any method, but I recommend the faster one. And now let's finally move on to the first full task from this topic. The content of the task is: for what range of gains k, the system shown in the figure is always stable. It should be assumed that the gain is greater than 0. At this point we can use what we have already done in the previous tasks. That is, we know what the inverse graph of the describing function looks like. We know the sinusoidal transfer function of a linear object. We should also know what the Nyquist plot of this linear object looks like. It has integration, so it starts at -infinity, and the two inertias tell us that the graph is in two quadrants of the coordinate system. Based on the task content, we want the closed-loop system to be always stable. Always stable, that means it is expected to be stable for any amplitude a. Therefore, the Nyquist characteristic cannot cover even a piece of the describing function inverse graph. In this task, one needs to find the range of gains for which both graphs will not intersect. In almost every problem of this type, you will need to use two equations, or one equation and one inequality. The first equation should be such that there is only one unknown variable in it, which unknown variable will be later substituted into the second equation or inequality. In this problem, the special point is the point -a divided by u. And since we are interested in a point on the real axis, the imaginary part of the sinusoidal transfer function should be equal to 0. We are only interested in frequencies, pulsations, greater than 0. Therefore, we have a frequency for which the Nyquist plot crosses the real axis. So, what condition must the real part of the sinusoidal transfer function meet? This value must be greater than minus a divided by u. However, we cannot leave this condition as a result, because in the task we also had the condition that the gain should be greater than 0. So, in the next task we assume that the system is given The first part of the task is to calculate the range of gains k for which a limit cycle will occur in the system. The second part of the task is to calculate the limit circle parameters for Of course, we assume that the amplitude is greater than small a. The formula of the describing function inverse for this nonlinear element is also given in the task. Now let's draw both graphs in the plane of a complex variable. First, a plot of the describing function inverse. the real part tends to minus infinity, and the imaginary part is the same. Let's also draw a Nyquist plot for a second-order inertia object. This time we want a limit cycle to occur, that is, we want both graphs to intersect. So what should be the first condition here? What equation will give us only one unknown variable? It happened that someone suggested equation of imaginary parts of both graphs. But in this task it is not enough, because we may have the following case. And we see that as a result of the equation, we would obtain two real solutions, but neither of these solutions means the intersection of the graphs. However, now I think that if the second condition was the real part less than 0, maybe it would work. Okay, let's check it. I'm curious whether it will work out for us. So let's compare the imaginary parts of both graphs. Unfortunately, this problem cannot be solved this way because we have more than one unknown in this equation, omega and k, and on the other hand, we would have to have specific values to use the roots function, and here we do not have exact parameter values. At this point, I would like to draw your attention to the content of tasks that may be conditional. In such tasks, in the first part one should, for example, check whether a limit cycle occurs, and the second part should only be solved if that limit cycle occurs, and then additional data should be used. This additional data cannot be used when solving the first part of such task. Okay, back to the condition that must be met for intersection to occur. Please look at the imaginary axis and at the points of both graphs on the imaginary axis. If the Nyquist characteristic intersects the imaginary axis above the second graph, there will be no graph's intersection. And if the Nyquist characteristic crosses the imaginary axis under the second graph, a limit cycle will occur in the system. Hence, the first condition is to equate the real part to 0 to obtain the intersection with the imaginary axis. And now the imaginary part must be below the graph of the describing function inverse. And this is the answer to the first part of the task. In the second part of the task, we need to calculate the parameters of the limit cycle. After substituting the parameters from the task content into the condition we have just written, we see that this limit cycle will occur. I will compare both formulas after substituting the parameters. We have two unknowns, amplitude A and omega. We start by equation of both imaginary parts to have one equation with one unknown. and here we need to find the roots of the fourth degree equation. We will use the roots command for this. You will also be able to use the roots function during the test. I will give you two pieces of paper on which you can enter the arguments for this function. When I receive such a piece of paper, I will calculate it on the computer and return the piece of paper with the real roots written. We got two solutions. How to interpret this? Do we have two intersection points of the graphs? This is a direct result of the drawing we see here. But which of these frequencies, pulsations, relates to the intersection of the characteristics? Let me remind you that in Nyquist plots, we get closer to the origin of the coordinate system as the frequency increases. So this higher value is interested for us. If the solution of the task is the frequency value, please remember to write the unit. Now we compare the real parts. And this is the second parameter of the limit cycle. I usually just mention the last task to look at the script and see what's going on, but since I have more time on the recording, we will solve a complete task of this type here. Suppose we have a nonlinear system where the nonlinear element is an ideal three-position relay and the transfer function of a linear object is the parameters are equal to the formula of the describing function inverse is the task is to calculate the range of amplitudes for which the closed-loop system is stable. Let's start by drawing the characteristics. The amplitude must be greater than small a to cover all specific points on the static characteristic. We therefore have a situation in which both the beginning and the end of the characteristic are at minus infinity. The static characteristic has no hysteresis, so the entire graph is on the real axis. We are therefore dealing with a two-way graph. This information would be enough to solve the problem, but let's try to find a specific point at which the characteristic turns back. If we consider the value on the real axis depending on the value of the amplitude A, the graph would look something like this. To find the vertex, we would have to calculate the derivative with respect to the amplitude and equalize the result to 0. So let's do exactly that. And this should be equated to 0. But the numerator doesn't look very friendly, so I will multiply it by the square root . We were able to do this because the content of the task implies the assumption that and using this assumption, we know that the denominator is greater than 0, so we can focus on the numerator. The amplitude is greater than small a, so it is also greater than 0. We already know at what amplitude the graph turns back. Now we just need to find at what point it is. It worked. Therefore, we can supplement our chart with other information. Now the Nyquist plot for a second-order inertia with integration object. Again, we start by calculating the frequency at which the Nyquist plot crosses the real axis. And now we equate both real parts. Of course, you can substitute the parameters earlier but I'm already used to calculations using parameters. The amplitude must be greater than small a, that is, greater than 1. Therefore, we have two intersections of both graphs for a frequency of 1/2 radian per second and for two different amplitude values. Let's go back to the drawn characteristics for a moment. We must provide the range of amplitude values for which the closed-loop system is stable. This means those fragments that are to the left of the Nyquist plot. Hence, and this is the solution of this task. Thank you very much for your attention and have a nice day.